Look at a solid steel I-beam bending under massive industrial pressure. It yields and deforms, but it does not snap. This malleability emerges as microscopic errors migrate through the crystal lattice. These line defects are called dislocations. They act as moving boundaries that allow entire planes of atoms to shear and slip. To see why that steel eventually resists bending and becomes rigidly hard, we have to scale down. We have to track how sub-nanometer anomalies dictate the ultimate failure point of massive infrastructure, like bridges and airplane wings. Macroscopic material strength follows the geometric mobility of these atomic-scale defects. This slide maps out the core mechanics of dislocations and microstructures. We will start by observing how individual atoms interact with empty spaces in the lattice structure. Next, we will define the specific three-dimensional steps these dislocation lines take as they navigate the crystal. Finally, we will establish how those microscopic steps interact with physical barriers to generate mechanical drag. By building this model from first principles, we can prove step by step how localized atomic friction scales up to system-wide material resistance. The foundation of this model relies on a specific movement called climb. Climb occurs when a dislocation line moves perpendicular to its normal slip plane. This diagram illustrates climb and lattice vacancies. In positive climb, an atom on the dislocation line moves vertically upward to fill a vacancy right above it. When the atom shifts into that gap, the vacancy is annihilated, shifting the entire horizontal plane upward. Negative climb is the exact inverse. Here, an atom on the dislocation line moves downward, dropping out of its current plane entirely. By leaving its original position, that downward-moving atom generates a brand new vacancy in the lattice. Because this climb process alters the local mass of the plane, either absorbing or emitting atoms, it is classified as non-conservative motion. Non-conservative climb strictly requires empty spaces to physically migrate through the crystal. That makes it a temperature-dependent bottleneck for atomic movement. In a physical metal, dislocation lines are almost never perfectly straight. They contain sub-nanometer steps that shift their trajectory. Regardless of the shape these steps take, the fundamental direction of the atomic displacement, the Berger's vector, remains constant. This graphic shows the two types of atomic scale steps. On the left, we have jogs. These segments move vertically, leaving their original atomic plane. On the right are kinks. These segments shift their position horizontally, but remain within the same slip plane. This table compares their properties. Looking at their formation, jogs are created when dislocations intersect or climb, while kinks are created by local shifts. The functional difference is severe. Kinks facilitate movement, while jogs act as physical hindrances. The 3D geometry of these steps governs the physical mobility of the dislocation. Kinks maintain their position securely within the original slip plane. This chart maps the Peierls-Nabarro energy barrier. This is the intrinsic frictional resistance of the atomic lattice that any dislocation must overcome to move forward. The horizontal distance marked B is the spacing between these energy peaks. Moving a rigid, perfectly straight dislocation line over that entire energy wave all at once requires massive applied stress. The kink offers a more efficient path. Rather than moving the whole line forward simultaneously, the kink propagates laterally. By zipping laterally across the line, the kink incrementally overcomes the Peierls-Nabarro barrier, facilitating rapid glide. Jogs do not have this luxury. Because they step out of the plane, they create different effects depending on the character of the primary dislocation line. Take an edge dislocation. The primary line and its Berger's vector are already perpendicular to each other. This graphic demonstrates the outcome. When a jog forms on an edge dislocation, the blue line and the pink Berger's vector remain perpendicular, even as the red step moves vertically. Because the step shares the geometric character of the primary line, it can glide seamlessly alongside it. Now look at the screw dislocation on the right. A screw dislocation line is by definition parallel to its Berger's vector. When an out-of-plane jog forms here, it forces that specific vertical step to run perpendicular to the Berger's vector. The mechanics are strict. Any dislocation segment perpendicular to its Berger's vector possesses edge character. That tiny step now behaves under a different set of rules than the rest of the line. This diagram outlines the resulting mechanical trap. The blue plane, defined by the dislocation line and its Burgers vector, represents the natural glide path for the primary screw defect. Sitting right in the middle is step AB, which possesses edge character. Because step AB is an edge segment, its natural slip plane is geometrically incompatible with that blue plane. It is physically restricted from gliding forward on that surface. When the main screw dislocation attempts to glide foreglide on a blue plane, it pulls the rest of the defect with it. This creates a deadlock. The main segment wants to glide, but step AB acts as a fixed anchor, refusing to move in that direction. There is only one escape route. To move forward with the line, step AB must abandon glide and move vertically out of its plane. This is climb. It requires the slow, energy-intensive absorption or emission of point defects. Forcing this tiny step to climb creates a localized anchor point. It exerts a severe drag force that bleeds energy from the system and grinds overall motion to a halt. How does this localized drag translate to the macroscopic strength of an I-beam or an airplane wing? This workflow charts the macroscopic result. As a material deforms, millions of active dislocations intersect with each other like violently tangling wires. These intersections randomly chop up the lines, generating a high density of new out-of-plane jogs on screw dislocations. Every one of those new jogs acts as a severe, climb-dependent anchor. The dislocations are pinned down, forcing them to bow out and physically multiply to bypass the resistance. The system rapidly exhausts the supply of vacancies needed for climb, effectively locking the dislocations in place. This exponential increase in locked dislocations manifests physically as increased yield strength and massive deformation resistance. The structural integrity of engineered metals is governed by the geometric inability of microscopic screw dislocation jogs to glide.